All right, let's just dive right into this. If you look around right now, literally every piece of tech you rely on, your phone, your laptop, the servers running the internet, owes its entire existence to one tiny foundational building block. Today, in this explainer, we're demystifying exactly what that is: the Bipolar Junction Transistor, or BJT for short.
There's a quote from our source material that I think just perfectly sets the stage here. It says, "The invention of the transistor was the beginning of a technological revolution that is still continuing." And it's so true. Every complex electronic system we use today is basically a direct outgrowth of this early semiconductor development. That's why getting a handle on the BJT is absolutely crucial. We are literally looking at the DNA of the digital age.
So, here's our roadmap for this explainer. We'll start with the transistor revolution, then break down the anatomy of a BJT and see how we bring them to life. After that, we'll hit the key characteristics and parameters. And finally, wrap up with operating regions and limits.
Section 1. Anatomy of a BJT. Exploring the physical structure.
So what actually is it? Well, by definition, a BJT is a three-terminal device. It's built using three specifically doped semiconductor regions, and we call these the emitter, the base, and the collector. These three areas are separated by two internal PN junctions. Now, fun fact, the word bipolar here, it just means the transistor uses both holes and electrons as current carriers. It's a real team effort.
Because of that physical setup, we end up with two basic variants, the NPN and the PNP. You can easily spot the three leads: E for emitter, B for base, and C for collector. And hey, here's a super handy tip for reading these schematics. If you check out the arrow on the emitter inside the symbol, it always points in the direction of conventional current. Good little trick to remember.
Section 2. Bringing BJTs to life, operation and biasing.
Okay, so how do we actually make this thing work? For a BJT to operate properly, especially if we're using it as an amplifier, we have to apply specific external DC voltages. This is a process called biasing. The specific setup we need here is called forward-reverse bias. Basically, that just means your base emitter junction has to be forward biased, while your base collector junction sits there reverse biased.
When you lock in that forward-reverse bias, a pretty wild physical journey kicks off inside the silicon. Step 1. The heavily doped emitter injects a massive wave of free electrons. Next, those electrons slam into the base. Now, the base is purposefully designed to be super thin and lightly doped, so it acts kind of like a delicate control valve. Finally, as those electrons push through that base valve, the positive voltage of the collector region violently sweeps them right across the reverse bias junction.
Seeing how this plays out internally really brings those steps into focus. Think about the total emitter current entering the device. As it tries to pass through that tiny, thin, p-type base region, only a tiny fraction of those electrons actually recombine with holes to create our external base current. The vast majority of those free electrons, they just rush straight through, getting completely swept up into the collector.
Section 3. Key characteristics and parameters. The vital signs.
All right, let's translate that physical flow into some math, starting with the fundamental BJT current equation. Based on what we just talked about, the emitter current, that's capital I, subscript E, is our total current. So naturally, it's exactly equal to the sum of the collector current plus the base current. And always keep that physical picture in your head. The base current is just an incredibly small fraction that splits off from that massive emitter flow.
This leads us right into two vital ratios we use to measure how a transistor behaves. First up is DC beta. This is the ratio of the DC collector current to the DC base current. Think of it as our current gain. On the flip side, we have DC alpha, which is the ratio of collector current to emitter current. Now, because that collector current is always slightly less than the emitter current, thanks to that tiny base current splitting off, alpha is literally always just a hair under 1, usually hovering around 0.95 to 0.99.
But DC beta, that is where the real magic happens. Typical values for beta can range anywhere from less than 20 all the way up to 200, or honestly, even higher. This number is essentially the BJT's superpower. It means that a ridiculously tiny trickle of base current can be multiplied by up to 200 times to control a massive, powerful collector current.
So how exactly do we model this superpower mathematically in a circuit? Well, on the input side, it just acts like a standard forward bias diode, which represents our base emitter junction. But the output side acts as a dependent current source. And the cool part is that this current source is driven entirely by the base current, multiplied by that powerful DC beta factor we were just talking about.
Now, I have to burst the bubble a little bit here because as with everything in the real physical world, beta is not some static magic number. If we look closely at its characteristics, it actually fluctuates quite a bit. It varies depending on how much collector current is flowing. It changes directly with the junction temperature, so if it gets hotter, beta goes up. And crazily enough, because of manufacturing tolerances, beta will even vary between two identical-looking transistors pulled from the exact same batch. No two are perfectly alike.
Section 4. Operating regions and limits, pushing the boundaries.
To really push these boundaries, engineers use collector characteristic curves to map out exactly how a transistor behaves across different voltages and currents. If you map it out, you'll see this wide flat area in the middle of the graph. We call this the active region. For a given base current, the collector current shoots up and then just levels off. Once it flattens out, that collector current becomes mostly independent of the collector-emitter voltage. It reaches a completely stable state.
Now, when we drop this component into a specific circuit, we can draw what's called a DC load line straight across those characteristic curves. This straight path visually maps out the absolute limits of that specific transistor circuit. One end of the line marks cutoff, and the other end marks saturation. Everything the transistor can possibly do in that circuit happens somewhere on that line.
Let's actually define those two extremes, starting with saturation. Saturation is what happens when the BJT is pushed to its absolute maximum limit. Both the base emitter and the base collector junctions become forward biased. At this point, the collector current hits a hard ceiling dictated by the external circuit. You could pump in way more base current, and it wouldn't increase the collector current at all. For all intents and purposes, the transistor is completely 100% on. Then, in stark contrast, we have cutoff. This is the state where your base current is dropped down to zero. Neither junction is forward biased. The flow of majority carriers just completely stops, which creates what is essentially an open circuit between the collector and the emitter. So in this state, the transistor is completely off.
Honestly, the best way to think about these two extreme states is by using a simple mechanical analogy. When the BJT is in cutoff with zero base current, it acts exactly like an open switch. Absolutely nothing flows. But when we pump in enough base current to drive it hard into saturation, it acts just like a closed switch, letting the maximum possible current flow right through the collector circuit.
Of course, at the end of the day, this is still a delicate physical piece of silicon. Datasheets will always specify maximum transistor ratings for a reason. If you decide to push the voltages or the maximum collector current or the total power dissipation beyond these strict limits, well, you're going to permanently damage or completely fry the crystalline structure of the transistor. So, respect the datasheet.
Section 5. Conclusion. The power of the switch.
We've seen how, just by controlling a tiny base current, we can force a BJT into cutoff, making it act as an open switch, a 0, or drive it into saturation, acting as a closed switch, a 1. So I want to leave you with this thought to take away from our explainer today. If a single BJT operates as a reliable open or closed switch, what happens when you figure out how to wire millions, or literally billions of them together on a single chip? Well, you get the binary foundation for all modern digital computers. And that technological revolution, it's still continuing today.